Module 2, Lecture B, Writing Functions. By the end of this lecture, you will be able to define Python functions that encapsulate common mechanical engineering formulas, use parameters and return values to make calculations reusable across different cases, and test functions with known examples to confirm correct engineering behavior. Function basics. Defining functions. In mechanical engineering, functions package repeated calculations such as stress or strain estimates into reusable tools. Clear, purpose-driven function names make scripts easier to understand, check, share, and maintain over time. A good function should handle one clear task, such as applying a specific engineering formula. This makes the code easier to understand, test, and check for errors. Keeping each function focused also creates a direct link between the code and the engineering logic, making results easier to trace and compare with expectations. When defining engineering functions, focus on the physical quantity being calculated, the required inputs, and the expected result. A well-named function should reflect its output and follow the appropriate engineering formula, such as stress from force and area, or deflection from load and stiffness. This makes calculations clearer, more consistent, and easier to reuse in tasks like lab data reduction or repeated design analysis. Python code. Defining functions. Functions help package repeated engineering calculations, so they can be used efficiently. Parameters supply the needed inputs, and return values let the computed results be reused elsewhere. The axial stress function takes a force in newtons and an area in square meters, then calculates stress in pascals by dividing force by area. It returns this value so the same calculation can be reused with different inputs. The function calculates stress in pascals by dividing force in newtons by area in square meters. Returning this value makes the function reusable for different inputs and contexts. The spring deflection function calculates how far a spring stretches or compresses under a load. It uses the load and the spring stiffness as inputs, finds the deflection by dividing the load by the stiffness, and returns that value for reuse in other calculations. The function calculates deflection in meters by dividing the applied load in newtons by the stiffness in newtons per meter. The result can then be reused in later calculations or comparisons. For testing, we use a force of 12,000 newtons and an area of 0.003 square meters. These known inputs help verify that the axial stress calculation function produces the expected result. The axial stress function calculates stress by dividing the applied force by the cross-sectional area. The result is stored and then displayed with pascals as the unit. Set the expected stress to 4 million pascals as the manual reference value. Then compare the calculated stress with this expected value and print whether the test passed. This true or false result helps confirm that the stress calculation function is working correctly. To set up the spring deflection calculation, we use a load of 500 newtons and a spring stiffness of 20,000 newtons per meter. These two inputs define the force applied to the spring and how strongly it resists deformation. The spring deflection function is called with the load and stiffness values to find how far the spring compresses or stretches. It calculates deflection as the load divided by the stiffness, then prints the result in meters. The expected spring deflection is set to 0.025 meters based on prior calculations or theory. The test then compares the calculated deflection with this expected value and reports whether they match. If they are equal, the test passes, confirming the function works as intended. This script demonstrates two simple engineering calculation functions. One finds axial stress by dividing force by area, and the other finds spring deflection by dividing load by stiffness. It calculates an axial stress of 4 million pascals and a spring deflection of 0.025 meters. Both results are compared with expected values, confirming that the functions work correctly. Function parameters. Function parameters let one function work with different input values, so the same calculation can be reused in many situations. In mechanical engineering, this means formulas can adapt to changing conditions, such as beam length or material strength, without rewriting the logic each time. By separating the calculation from the specific data, parameters make functions more flexible and easier to apply across related engineering problems. Clear parameter names make engineering functions easier to use correctly and reliably. They should indicate the physical quantities the function expects, such as values for pressure drop or natural frequency calculations. Good names act as built-in documentation, connect the code to engineering meaning, reduce mix-ups between similar values, and help collaborators understand the required inputs quickly. When designing a mechanical engineering function, choose carefully which quantities are inputs and which are treated as constants. This affects how flexible and reusable the function will be, such as whether gravity is fixed or allowed to vary. Good parameter choices require both programming skill and engineering judgment, so the function matches the physical assumptions behind the formula. Python code. Function parameters. Functions can take changing engineering inputs, with parameters identifying the physical quantities needed for a calculation. By returning results, functions make those calculations reusable. The axial stress function calculates stress from a given force and area. Before doing the calculation, it checks that the area is positive. If the area is 0 or negative, it raises an error to prevent an invalid result. The function calculates stress in pascals by dividing force in newtons by area in square meters. This gives the force applied per unit area, a key engineering measure, and the computed value is then returned for later use or analysis. The torque function calculates shaft torque from force and radius. Before doing the calculation, it checks whether the radius is negative and raises an error if so, since a negative radius is not valid. The function calculates torque in pound-inches by multiplying the force in pounds by the radius in inches. It returns this value as the measure of rotational force for later use. The axial stress function is used to calculate stress for two materials by entering each component's force and cross-sectional area. For steel, the inputs are 12,000 newtons and 0.0008 square meters, while for aluminum, they are 7,500 newtons and 0.0005 square meters. The resulting stresses, in pascals, can then be compared to see how each material responds under its given load and area. The torque function is called with a force of 35 pounds and a radius of 6 inches. It multiplies these values to calculate torque in pound-inches, showing how the function works with imperial units. The test sets an expected steel stress of 15 million pascals and compares it with the calculated result. If the two values match, the check passes, showing that the stress calculation works correctly for this known example. The output reports the calculated stresses for steel and aluminum in pascals, then gives the shaft torque in pound-inches. It also checks whether the steel stress matches the expected value and reports whether that validation passed. The script defines simple engineering calculations for axial stress and torque, with checks to ensure the area is positive and the radius is not negative. It then computes stress values for steel and aluminum, calculates shaft torque, and verifies that the steel stress equals 15 million pascals. Finally, it prints the stress results in pascals, the torque in pound-inches, and whether the stress check passed. Returning results. Returning results makes a function reusable and useful beyond a single calculation. In engineering programs, a function that computes values such as stress, power, or beam deflection should send the numerical result back to the program so it can be displayed, stored, compared, plotted, or used in later calculations. This separates calculation from output, making the function more flexible across different situations. In mechanical engineering, returned results are important because one calculation often becomes the input for the next. For example, an area calculation can support a stress check, and a mass flow rate can support heat transfer analysis. Clear outputs make each step a dependable building block, helping engineers break complex problems into manageable parts. When designing an engineering function, make its return value clear, meaningful, and predictable. Decide whether the calculation should produce one result, such as a stress value, or multiple related results, such as force magnitude and direction. The output should match the physical meaning of the formula and be useful for later analysis, which makes the function easier to test and more reliable. Python code, returning results. Functions can return results that are reused in later engineering calculations. In this example, simple stress functions show how returned values support design checks. This function takes a circle's diameter in meters and returns its area in square meters. It uses the standard circle area formula expressed in terms of diameter, multiplying pi by the diameter squared and dividing by 4. This function computes axial stress by dividing the applied force by the area carrying that force. It uses force in newtons and area in square meters, and returns the resulting stress in pascals for use in further analysis. The engineering strain function calculates deformation strain by comparing the change in length to the original length. It takes the change in length and the starting length as inputs, divides the change by the original length, and returns the resulting strain value for use in later analysis. We begin by recording the rod's key input values, a diameter of 0.02 meters, an applied force of 5,000 newtons, and an original length of 2 meters. These values are needed to calculate the cross-sectional area, axial stress, and engineering strain during deformation. The calculation begins by recording the rod's 1 millimeter elongation. The rod's cross-sectional area is found from its diameter using the circular area function, and the axial stress is then calculated from the applied force and that area. Together, these values help describe how the rod behaves under the load. The code converts rod stress from pascals to megapascals to make the value easier to work with. It then computes engineering strain as elongation divided by the rod's original length, giving a dimensionless measure of deformation. It also stores an expected area value to check the calculated area for accuracy. The calculation first verifies that the rod area matches the expected value within a very small tolerance, confirming numerical precision. It then displays the rod area to 6 decimal places and the axial stress in megapascals to 2 decimal places, giving clear results for checking and analysis. This function calculates axial stress by dividing an applied force by the cross-sectional area. It uses force in newtons and area in square meters, producing stress in pascals. the computed stress value is returned for use in later calculations or analysis. This script computes basic engineering properties for a stressed rod. It finds the circular cross-sectional area from the diameter, uses that area to calculate axial stress, reports the stress in megapascals, and calculates engineering strain from elongation divided by original length. It also checks the area against an expected value and prints the results, including whether the accuracy test passed. Reusable formula functions. Parameter inputs. Parameter inputs let a function receive the data it needs for a calculation, instead of relying on fixed values. In mechanical engineering, this makes one function adaptable to different cases, such as stress or heat transfer calculations across different materials and conditions. By separating the calculation method from specific input values, functions become reusable, consistent tools for engineering computing. Clear parameter inputs make engineering functions easier to understand, reuse, and trust. Each input should have a meaningful role and specify what values, assumptions, and units are expected, such as load type, length, and material stiffness in a shaft deflection calculation. Well-designed functions connect engineering assumptions to computation and reduce errors when different team members apply the same method. Parameter inputs let engineers reuse the same calculation across different design scenarios by changing only the input values. This makes it faster to test alternatives, verify results, and keep computational models organized and consistent. Learning to choose good parameters supports a modular approach, helping learners build reusable tools for engineering analysis. Python code, parameter inputs. Functions take in values through named parameters, with each parameter representing a specific engineering quantity. The function can then return a result, making the calculation reusable in different situations. The normal stress function calculates stress by taking a force in newtons and an area in square meters. It divides the force by the area to produce the stress in pascals, then returns that value so the calculation can be reused with different inputs. This function uses Hooke's law to find how far a spring stretches or compresses under an applied force. It takes the force and the spring stiffness as inputs, calculates deflection by dividing the force by the stiffness, and returns the result in meters for use elsewhere in the program. The normal stress function is used to find the stress on both a steel bracket and an aluminum panel from their applied forces and areas. The results are first calculated in pascals, then converted to megapascals by dividing by 1,000,000. This makes the stress values easier to interpret in an engineering context. We calculate spring deflection for the same 400 Newton force using two stiffness values, 20,000 newtons per meter for a soft spring and 50,000 newtons per meter for a stiff spring. Each result is first found in meters, then converted to millimeters by multiplying by 1,000. This makes the deflection values easier to present in practical engineering units. The normal stress function is tested using a force of 1,000 newtons and an area of 1,000th of a square meter. The result should be very close to 1,000,000 pascals, and an assert statement checks this by allowing only a tiny difference. If the test passes, nothing is printed, confirming the function works correctly unless an error occurs. The example prints reusable parameter inputs by reporting stress values for steel and aluminum components in megapascals, then deflection values for soft and stiff springs in millimeters. Each value is formatted to an appropriate precision, and the output ends by confirming that a known stress test passed. This script uses simple engineering functions to calculate normal stress and spring deflection. It finds stress for steel and aluminum by dividing force by area and reports the results in megapascals. It also uses Hooke's law to find deflection for soft and stiff springs, reported in millimeters. A known stress result is checked with an assertion, and the script ends by confirming that the test passed. Parameter return flow. In mechanical engineering, parameter return flow describes how a function receives data, processes it, and returns a useful result. This helps handle calculations that change with conditions, such as material properties or speed. A well-designed function reduces repetition by taking inputs, performing the needed calculation, and returning a value that can be reused, such as estimating stress from force and area. Parameter return flow clarifies the difference between what a function receives and what it produces. Inputs provide the data needed for the function to run, while the return value gives the processed result. Keeping these roles separate makes functions reusable across different cases by changing the inputs while preserving the same core logic. This supports flexible, organized computational models as engineering workflows become more complex. Explicitly returning results from functions makes engineering programs clearer, more reliable, and easier to connect. Returned values can be stored, compared, plotted, or used in later calculations, such as applying a computed torque to a safety factor. This keeps each function focused on one task, while allowing results to support larger design decisions. Python code. Parameter return flow. Functions make engineering formulas reusable by packaging the calculation in one place. Parameters bring the specific case information into the function, and return values send the computed result back out. The axial stress in megapascals function calculates stress from a given force and area. It takes force in newtons and area in square millimeters, divides the force by the area, and returns the resulting stress value for use elsewhere in the program. The shaft torque function calculates torque in newton meters using force and radius as inputs. It multiplies the force in newtons by the radius in meters, then returns the resulting torque so it can be used elsewhere in the program. The safety factor function compares a material's allowable stress with the actual stress it experiences. It calculates this by dividing the allowable stress by the actual stress, then returns the result. This value shows how much stronger the material or structure is than the load it is currently facing. The setup defines three key inputs for the calculations: a load of 12,000 newtons, a cross-sectional area of 300 square millimeters, and an allowable stress of 250 megapascals. These values will be used to calculate stress, torque, and the safety factor. The process calculates and stores three key results. It first uses the axial stress function with the load and area to find stress in megapascals, then uses the shaft torque function with the load and radius to find torque in newton meters. Finally, it uses the allowable stress and calculated stress to determine the safety factor for later use. The output first confirms that the force and area inputs were entered, then presents the calculated results in clear units. It shows stress to 1 decimal place in megapascals, torque to 1 decimal place in newton meters, and the safety factor to 2 decimal places. Together, these messages clearly summarize the key parameters and results from the calculations. The axial stress function is reused for a new case with a force of 8,000 newtons and an area of 200 square millimeters. The resulting stress is saved as a second stress value and printed to 1 decimal place in megapascals. This script shows how functions can organize common engineering calculations for axial stress, shaft torque, and safety factor. Each function takes input values, performs a simple calculation, and returns a result, demonstrating how parameters flow into functions and computed values flow back out. Using the given force, area, radius, and allowable stress, the script reports a stress of 40 megapascals, a torque of 9.6 newton meters, and a safety factor of 6.25. It also repeats the stress calculation with different inputs to show that the same function can be reused. Return values. Return values make functions useful beyond a single calculation by allowing results to be stored, shown, or used in later computations. In mechanical engineering, this is important because one result often guides the next step, such as comparing calculated stress with material limits. Outputs from functions for stress, heat transfer, or torque can then feed into larger engineering workflows. A function's return value should be chosen so its output stays predictable across different inputs. In engineering calculations such as beam deflection, the function should consistently return the deflection, so results can be checked against limits and compared across designs. This makes the function more adaptable, reliable, and easier to reuse. Return values make a function's purpose clear by having it output the main quantity it is meant to calculate, while leaving unrelated tasks to other parts of the program. This makes functions easier to test, reuse, and trust. In engineering workflows, precise return values can feed later calculations, such as using velocity to determine flow behavior and pressure loss. Clear outputs help functions act as reliable building blocks in larger analyses. Python code, return values. Functions can return engineering results that are reused in later design checks. In this example, returned values are used to evaluate stress and safety. The calculate stress function takes force in newtons and area in square meters, then finds stress by dividing force by area. It returns the result in pascals, so the value can be used elsewhere in the program. The calculate safety factor function compares allowable stress with actual stress by dividing the allowable pascals by the actual pascals. The returned value shows how much margin the material has under the current load, helping indicate whether the design is safe. We set up the key inputs for a simple bracket design, a force of 2,500 newtons, applied over an area of 0.0005 square meters, with an allowable material stress of 120 million pascals. These values are used to calculate the stress and judge whether the design is safe. The process first calculates stress from force and area, giving a value in pascals. It then uses that stress with the allowable stress to find the safety factor and judge whether the design is safe. Finally, the stress is converted to megapascals by dividing by 1 million, making it easier to compare with engineering standards. The design is checked by comparing its safety factor with the minimum required value of 2, producing a true or false result for whether it is safe. The program then reports the calculated stress in megapascals and the safety factor, both rounded to 2 decimal places, followed by a clear statement of whether the design meets the safety requirement. This script estimates the stress on a bracket and checks whether the design is safe. It calculates stress from the applied force and area, compares it with the allowable stress to find the safety factor, and reports the stress in megapascals for readability. The design is considered safe if the safety factor is at least 2, and the results are printed to the console. Function testing. Known value checks. Known value checks test a function using inputs whose correct results are already known. These expected results may be verified by hand, taken from trusted sources, or drawn from validated engineering worksheets. In mechanical engineering, this helps confirm calculations such as beam deflection, stress conversion, or pump power under standard conditions, making it easier to identify errors in the function itself. Choose known value checks deliberately, using simple cases where mistakes are easy to spot. For example, a tank volume calculation should work for dimensions with an expected result, and a thermal expansion calculation should show no expansion when temperature change is 0. These checks help confirm both the arithmetic and whether the function matches the system's physical behavior. Known value checks are strongest when they test both normal inputs and edge conditions. Typical cases confirm that a function works as expected in everyday use, while edge cases expose hidden problems with values like 0, very small numbers, or limits. Using these checks consistently helps ensure functions are reliable for design and safety decisions. Python code. Known value checks. Use known values to check engineering functions, since simple cases can quickly expose formula errors. Edge cases are also important because they show whether the function behaves sensibly under physical limits. This function calculates a cylinder's volume using its radius and height in meters. It applies the standard formula, pi times the radius squared times the height. Pi is built directly into the function to support accurate calculation without using external libraries. This thermal expansion function estimates how much a material's length changes when its temperature changes. It uses the initial length, the material's expansion coefficient, and the temperature change, then multiplies them to find the change in length. Known checks are stored as labeled tuples to test whether the functions give expected results. One check verifies the cylinder volume calculation for a 1 meter radius and 2 meter height, expecting about 6.28. Another confirms that thermal expansion is 0 when the temperature change is 0. Together, these checks compare computed outputs with known values to help validate the functions. This comparison function checks a calculated value against a trusted expected value. It finds the absolute error, compares that error with a chosen tolerance, and labels the result as pass or fail. It then returns a short formatted message with the label, status, and error, helping confirm whether a calculation matches a known benchmark. The code verifies two engineering functions using known expected results and a tolerance for error. It checks a cylinder volume calculation and a thermal expansion calculation, then reports whether each one passes or fails. Together, these tests help confirm that the functions produce reliable results, including under edge conditions. The stress psi function calculates stress in pounds per square inch by dividing the applied force in pounds by the area in square inches. This gives the force applied over a specific area, which is a basic calculation in engineering stress analysis. A simple hand calculation is used to check the stress result. The stress psi function divides a force of 1,000 pounds by an area of 2 square inches, giving an expected stress of 500. The check known value function compares this result with the expected value using a very small tolerance, then prints whether the check passed and reports the error. The script checks several engineering calculations against known expected results. It confirms that the cylinder volume calculation gives about 6.28 cubic meters for a 1 meter radius and 2 meter height, that thermal expansion is 0 when there is no temperature change, and that stress is 500 pounds per square inch for 1,000 pounds of force over 2 square inches. All checks pass within a very small tolerance, showing the calculation functions are working correctly.
Expected results.
Expected results are essential for meaningful testing because they define what a correct function should produce before the test is run. Engineers can determine these results through hand calculations or trusted reference data. In mechanical engineering, this matters because a function may appear reasonable while still giving incorrect values that affect design decisions. Comparing outputs to known results turns testing from simple observation into a check of correctness. Choose expected results that test the function's real engineering logic, not just whether it matches a number. Use simple, independently checkable cases, such as known force calculations or realistic thermal expansion data for well-documented materials. This helps reveal common mistakes, like unit errors or missing conversion factors, while ensuring the output makes sense in context. Expected results help build trust in functions by checking their outputs against known outcomes before using them in larger engineering tasks. That trust should depend on how complete the testing is, since a function may still fail in unusual or extreme cases. Defining expected results for both typical and edge cases supports computational accuracy and keeps the work physically meaningful. Python code. Expected results. Expected results are essential for testing engineering functions because they show whether calculations are producing the right answers. Using known answers helps catch formula errors, and small tests build confidence that calculations can be reused reliably. This code defines a reusable force calculation function. It takes mass in kilograms and acceleration in meters per second squared, then returns their product to calculate force in newtons using Newton's second law. The stress MPa function calculates stress in megapascals using a force in newtons and an area in square millimeters. It divides the force by the area and returns the result, giving the force applied per unit area. This is a common engineering calculation for evaluating material strength.
The test checks whether the force calculation is correct by comparing the result to an expected value of 50 newtons. It uses a mass of 10 kilograms and an acceleration of 5 meters per second squared, then verifies that the calculated force differs from the expected value by less than a very small tolerance. If the difference is within that limit, the test passes.
The test sets the expected stress to 25 megapascals, then calculates the actual stress by dividing a force of 5,000 by an area of 200. It compares the result with the expected value using a very small tolerance to confirm precision. The final result records whether the stress calculation passed the test. The output begins by noting that the functions are being tested against expected results. It then compares expected and calculated values for force in newtons and stress in megapascals. Each test also prints a pass or fail result based on an allowed error tolerance, making it easy to confirm whether the calculations are accurate. This script checks two engineering calculations, force and stress. It verifies that multiplying mass by acceleration gives 50 newtons, and that dividing force by area gives 25 megapascals. Each result is compared with the expected value using a small tolerance. Then the script reports whether the tests passed. Expected results. In engineering, a function must do more than run without errors. Its results must make physical sense. Expected outputs should be checked against reliable sources, such as hand calculations or textbook examples. For example, a stress calculation should match a known result within a reasonable tolerance, confirming that the formula and assumptions are correctly implemented.
When setting expected results, Use realistic engineering examples that can reveal errors such as wrong ratios or missing unit conversions. Estimate the answer before running the function, rather than judging it after seeing the output. For a heat transfer calculation, for example, choose plausible wall dimensions and temperature differences. Then, check whether the result matches physical reality. Expected results help keep engineering code reliable when functions are changed or combined. By comparing outputs with known correct cases, such as checking a beam deflection calculation, engineers can confirm that earlier behavior still works and avoid errors that could affect materials or cost. Over time, these checks build confidence and make testing a routine part of engineering computation. Python code, expected results. Functions should align with established engineering examples, and expected results should verify that the formulas were translated correctly. A small tolerance is used to account for minor floating point differences. The axial stress function finds the stress on an object by using the applied force and the area it acts on. It divides the force in newtons by the area in square meters to give stress in pascals. This is a basic engineering calculation for understanding how materials respond to loads. The percent error function measures how far a calculated value is from an expected value. It finds the absolute difference between them, compares that difference to the absolute expected value, and returns the result as a percentage. A known metric stress example is set up using a force of 10,000 newtons and a cross-sectional area of 0.005 square meters. These values give an expected stress of 2 million, which is used as a benchmark to check that the stress calculation function works correctly. Calculate axial stress by dividing the applied force in newtons by the area in square meters. Then compare the calculated stress with the expected value using percent error, based on the absolute difference divided by the expected value and converted to a percentage. A 1% tolerance is used to decide whether the result is close enough, allowing for small floating point differences. The code checks whether the stress error is within the allowed tolerance and uses that result to decide if the axial stress test passes or fails. It then prints the pass or fail status and reports the calculated stress value in pascals for reference. The center deflection function estimates how much a beam bends under a load applied at its center. It uses the load, beam length, modulus of elasticity, and moment of inertia, then applies the standard central point load deflection formula. In words, the deflection is the load times the length cubed divided by 48 times the modulus of elasticity times the moment of inertia. This example defines the key properties for a loaded beam: a 500 Newton load, a 2-meter length, a modulus of elasticity of 200 billion pascals, and a moment of inertia of 8.333 times 10 to the negative 6 meters to the fourth power. Together, these values describe the beam's loading, material stiffness, and resistance to bending. Set the expected deflection as the reference value, then calculate the actual deflection using the center deflection function with the load, length, modulus, and inertia. Compare the calculated result with the expected value to find the percent error. This shows how closely the function's output matches the reference and helps judge its accuracy. The beam deflection test passes if the calculated error is under 1%. The program reports whether the test passed or failed, then displays the calculated deflection rounded to 9 decimal places for clear feedback. The script checks two engineering formulas using known example results. It calculates axial stress as force divided by area, then calculates beam deflection for a centrally loaded beam using the load, length, modulus, and inertia. In each case, it compares the computed value with the expected value, checks whether the percent error is within a small tolerance, and reports whether the test passed along with the calculated result. In this lecture, you learn to define Python functions that encapsulate common mechanical engineering formulas, use parameters and return values to make calculations reusable across different cases, and test functions with known examples to confirm correct engineering behavior. In the next module, Module 3, we will go over none.
Thank you for your attention. See you all in the next lecture.